Mr. Erik Sauter holds a master degree in facility and process design from the Albstadt-Sigmaringen University. Since November 2019, Erik Sauter started his PhD studies at the Sustainable Packaging Institute with a focus on the process structure property interaction of bio-based surface functionalized polylactic acid-based multilayer films. As a scientist, he works within the European project BionTop since 2020. He will present principle of chemical grafting and effect of fatty acid grafting onto whey protein-based films. So thank you, Erik. Please, the floor is yours.
Thank you, Mara, for the short introduction. And I'd like to welcome you to the workshop, Eco-Funke workshop. I now want to present the principle of chemical grafting and the effect of fatty acid grafting onto whey protein-based films. I'd like to introduce you the content of my presentation. First, I want to present the SPI, the Sustainable Packaging Institute. Then I want you ongoing with the principle of chemical grafting. Then I want to present the two methods we used for chemical grafting. Then the current research results of the chemical grafting, and a short conclusion at the end of my presentation. The Albstadt-Sigmaringen University is based in the south of Germany near the Lake of Constance, and there you can see our new model factory, Sigmaringen, where you can find our new labs. As a part of the Faculty Life Science, the Sustainable Packaging Institute is, or short SPI, develops into research and teaching in 6 subject areas. And the main research focus are on sustainable packaging concepts for entire life science industry. These are the 6 subject areas of the Sustainable Packaging Institute: bioeconomic, raw materials, process design technology and design, functional materials, smart packaging like active and intelligent packaging, preservation and packaging, and bioeconomy and sustainability, concepts, assessment, and perception. After this short introduction of the Sustainable Packaging Institute, I want to continue with the principle of chemical grafting. The grafting of a polymer are described in the covalent attached process, which is irreversible, and the term grafting to approach means that the functionalized monomers directly react with the polymer or with the substrate. The chemical grafting technique is a technique to modify the surface of these monomers and to add a layer composed of fatty acids covalently to the surface of a substrate. This technique can be used to modify the surface of especially polar substrates. In our experiments, it's a whey protein layer. And there you can see a schematic diagram of this grafting process. There you can see the substrate with the different OH groups or functional groups and the fatty acid chlorides, and then the esterification and the covalent bounded fatty acids on the surface of the substrate. The motivation of this chemical grafting is that's a fast reaction. It's a reaction with efficiency, material efficiency. You had a hydrophobic surface and a high water vapor barrier, and less humidity sensitive of the oxygen transition rate, especially for the protein coating, because it's humidity sensitive. The objective of this of the chemical grafting is the nanoscale surface modification. There's highly material efficiency, and to achieve hydrophobic surfaces and low surface energy, improve the water vapor barrier and repellence coating. That's for easy emptying from packaging especially. and the thin layer do not influence the biodegradability or the recyclability. At the left side, you can see our schematic diagram of our experiment. You can see at the bottom the protein layer, the whey protein cast films, and the grafted fatty acids on the top, and there will be a repellent effect. The barrier effect is depending of the grafting density, and there you can see the reaction. There you can see the whey protein with the different functional groups, and the fatty acids that are heated, and then the reaction with the whey protein and the fatty acids are covalently bounded. For our experiments, we use 4 different reagents, the stearoyl chloride, the palmitoyl chloride, and the myristic chloride, and the palmitoyl anhydride. The palmitoyl anhydride is not so reactive than the fatty acid chlorides. The fatty acid chlorides for the fatty acid grafting process, the high length of fatty acid chains are preferred based on increasing in the hydrophobicity, so that the stearoyl chloride have the highest hydrophobicity. If we have a look at our 2 methods we use for our experiment, we use the transfer method via transmitter paper. There we dissolved petroleum ether and transfer the fatty acids to a transmitter paper, and then to the substrate, and the reaction is in an oven. Instead of the gravel printing technique, there's an upscaling of the fatty acid grafting process. The fatty acid chlorides are not diluted and not dissolved, and they are directly printed on the surface of our substrates. There you can see the transfer method via transmitter paper, the different process steps. First, we start with the fatty acid chloride solution in a solvent. Then we immersing the transmitter paper, and the vaporization. After that, we put them together and applying that to the substrate, and then the reaction is in an oven. We're writing different parameters like the fatty acid chlorides with different molecular weight. I show you 2 slides before. The concentration on solvent and type of the substrate in other experiments, and the grafting parameters like the temperature. And instead of the gravel printing technique, there you can see our printing form we used for printing the substrates. The fatty acids are not diluted and not dissolved, in contrast to the transfer. And there you can see at the right side microscopic view of the different printing plates we used. There you can see we have different printing plates. There you can see the decreasing volume of the grafting reagent on surface. And for these experiments, we used these printing plate. There you can see the printing plate. If we put them on the surface of the printing plate, and there you can see a video where we print them on the surface. There you can see on the video that we put the fatty acids onto the printing plate, and then we print the substrate, the fatty acids directly on the surface of the substrate. There you can see a textile. In our experiments, we used the whey protein. That's the same process. And after this step, we put them in an oven for several minutes. This was the 2 techniques we use for our experiments, the transfer method and the gravel printing technique. And now I want to present the first results, the current results of the BionTop project. There you can see at the right side a whey protein cast film, and in the diagram there are the water vapor transmission rate of the grafted whey protein films are illustrated with the transfer method. And next slide, I want to compare the transfer and the curve printing technique. But let's have a look at the results of the transfer method. There you can see the reference. It's the whey protein cast film without any coating, and we have heated the grafted whey protein films between 60 and 160 degree. We have with palmitoyl chloride, we have an BIF of 1.4. But however, it's no, if you have a look at the bars, we have no significant highs because of the high standard deviations. But if you have a look at the fatty acid chlorides, there we can see that with the myristoyl chloride, we have a BIF 1.5. With the palmitoyl chloride, we have a BIF of 3.0, and with the stearoyl chloride, we have a BIF of 4.8. This indicates that the water vapor barrier could be increased by both factors, by using fatty acid with higher chain length, like the stearoyl chloride, and using different grafting temperatures. If we compare,
excuse me, Erik, you have 5 minutes left. Thank you.
Okay, thank you. If we compare the transfer and the graver printing technique, there we can see in this diagram, there you can see the green bar is the reference, and there you can see the same bars like in the diagram before. There you can see the influence of the grafting temperature of the transfer method is highly dependent on the temperature. And if we have a look at the bars and results of the water vapor transmission rate of the whey protein cast films grafted with the graver printing technique, there you can see it indicates no dependence on the temperature, whereas the fatty acid grafting by the transfer method was highly dependent on the temperature. There we reached a BIF of 7.9. They might be due to the fact that the transfer method, the fatty acid chlorides need to transfer from the Whatman paper over gas phase to a substrate, and this is the reason why it is not dependent. The graver printing technique is not dependent. If we have a look at the repellent effect of the whey protein of the grafting, and in the diagram the contact angle are illustrated. There you can see the different processing temperatures we use for grafting. The contact angle of the whey protein films coated with palmitoyl chloride, and reference could not be measured based on the rapid spreading of the water drop, and it penetrates into the film. I will show you a video at the next slide. There you can see the rapid spreading of the water drop. And now to the results of the contact angle at 160 degree with the transfer method, we had reached contact angle about 100. And now I want to show you the video. There you can see we put in this experiment a water drop on the surface of our whey protein cast films. And there you can see it penetrates a few seconds into the whey protein cast film, and instead of the whey protein cast film grafted with palmitoyl chloride at 160 degree for 10 minutes, we have our repellent effect. There you can see the results I show you in the diagram. There we put an water drop on the surface, and there you can see the repellent effect of these of the grafted palmitoyl grafted whey protein cast film with palmitoyl chloride. Now I want to make a conclusion about chemical grafting onto whey protein based films. The fatty acid grafting of the whey protein films lead to a significant barrier improvement factor for both techniques, the transfer method and the cryo printing technique. It's an upscaling of the transfer method and grafting, chemical grafting, and we had a repellent effect of the grafted whey protein based films with the transfer method and the printing method. And there you can see these results. I show you in the video. There is a water drop on the surface on the non-grafted and the grafted whey protein films, and there you can see the clear repellent effect of the grafted whey protein based film. Thank you for your attention.
Thank you, Erik. Thank you for your presentation and for explaining us your advances in such interesting techniques of chemical grafting. We have four questions for you. I hope we have enough time. So the first one is, what was the thickness of the films for the WVTR measurement?
The thickness was 100 micrometers, and the layer was a nanoscale. The thickness of the whey protein cast films was 100 micrometers.
Okay, thank you.
Okay.
And then we have another one. The chloride fatty acids used were commercialized products?
Yeah, we use products from Sigma Aldrich to graft our substrates.